Okay, guys, this is the last dance. This is the last video. Um, I'm doing a giveaway though. I promised this back in Unit 3 on here. If you liked and commented down here, I put those names on the wheel generator, and whoever wins this spin gets something. DoorDash, lunch, a root beer, who knows? What do we get? What do we get? What do we get? What do we get? Who's it gonna be? Who's it gonna be? Oh, I had to be Christian. All right. Oh, congrats, Christian. We have a winner. All right. Round of applause. All right, we're gonna get going here, guys. Let me bring up Visualizer. All right. So, this is the last video. This is a crash course in everything calculus. We're gonna be going over the whole curriculum from the beginning to the end as much as I can. Obviously, you can't cover everything in one video, but I'm trying to cover basically all the big ideas that you should know. So as you're doing this, one thing I want to emphasize is like um, do not just watch it passively, right? This isn't We're not here to watch it passively. You're here to predict. I'm gonna Dora explore this. By that I mean I'm gonna ask you questions and I'm gonna ask you to fill it in and to test yourself because you got to push yourself. You can't just watch. If you learn anything this year, hopefully you learned that. Hopefully you learned like it's not a good enough just to watch the video, guys. You got to really follow through. All right, let's get started. So limits. This is one of the first things we learned. Uh, for limits, let's talk about what these mean. So when you have a limit as x approaches a with this little plus sign, this means that we do what? This is where you write it in. You approach from the right. With a negative sign, you approach from the left. And this is from both sides, right? Essentially, the P means approach from both. Okay, so like let's do some examples here. So for example, limit as x approaches, let's say 0 from the left would be I assume this is f, equals, that'd be 0 because as I approach 0 from the left, my y value is 0. As I approach from the right, my limit is 3. Okay, and so my limit overall, limit of f as x approaches 0 overall would be what? This is where we're getting to this question right here. You tell me, what is this limit right here? This limit does not exist. It does not exist because um, they don't meet. So if limit from left and right match, okay? So if the limits meet, it exists. So this does not exist. This exists. This exists. This exists. This one does not exist. Okay, got it? Definition of continuity. Definition of continuity says that limit as x approaches a from the left of f equals the output at a equals limit as x approaches a from the right of f. So it's continuous if all those three things are true. This point here is continuous. This point here is not continuous. This point here is not continuous, right? You can think of it very simply as like if there's a gap, it's not continuous here because the output does not equal the limit. Okay. Again, if you want more help with this, like there's plenty of delta you can do, so much review you can do. Um, I want to take some time to go over continuity. Oh, we're going to go over that in a second. But yeah, we're going to go over, sorry, we're going to go over differentiability in a second. But yeah, these are, yes, one thing I do want to cover though here, the different kinds of discontinuities. So this right here is called, let me different color. This is right here, this is a jump discontinuity. This is an asymptotic. I believe it's asymptotic. And then this one is a removable discontinuity. Okay, got it? All right, moving on. Here's like a little multiple choice question, just to practice. The figure above shows the graph of the function f, which of the following statements is true. So take a second, guys. See if you can do it. Okay, hopefully you've tried. The figure above shows the graph of f, yada, yada, yada. So the limit as x approaches 2 from the left equals f of 2. Okay, so as we approach 2 from the left, yep, I get to negative 1. And that is also the filled hole. So that is true. 1 is true. As we approach 6 from the left, it equals the limit from 6 from the right. So as we approach 6 from the left, that approaches as we approach 6 from the right. That is also true. Okay, even though this point appears down here, the limits are still the same. And then the limit as x approaches 6 equals f of 6. Well, this is false. The limit is negative 1, but the output is negative 3. So these do not match. That is false. So it's just 1 and 2 would be the answer, C. Okay. Differentiability. So that's continuity and limits. Differentiability is talking about can you take the derivative at the point. That's the gist of it. Can we take the derivative here? Can we take derivative? So you cannot at these points. So at a cusp, at a corner, you cannot. And when it's discontinuous, you cannot. And when it's a vertical tangent, you cannot. These are not differentiable, right? Be sure that's clear. Not differentiable. Okay? All these. All right? These are not differentiable. Points, like specifically here, here and here, right? That's where it's not differentiable. All right, so here's a little practice problem. Let f of x be a piecewise function defined below. At x equals 2 is the function is choose one of the following. So to be differentiable, so differentiability means that it must be continuous. Like it must be true. So whenever you check if it's differentiable somewhere, you want to check if it's continuous first. Like let's just start with that. Start with that. So right here, if I plug in a 2, it's kind of hard to tell if it's 2 squared or 2 to the third, but I think it's 2 squared. So 2 squared is 4, and 8 minus 4 is also 4. So it is continuous because when I plugged in the values, it was true. If this was an FRQ, you would use limit notation to do this, but we're in a bit of a rush here, so I'm not going to do that. For differentiable, the derivatives also have to match. So the derivative here would be, so it's 2x here, and then it's going to be just negative 2 here. And when I plug in a 2 here, you can see that that will be a 4. Right, so these are like, this is f prime of x, if that's not clear. This will be a 4, and then that would be a negative 2 when I plug in a 2. Right, so they're not differentiable. The derivatives don't match, but it is continuous. So it's continuous but not differentiable. This is impossible. C is impossible because if it's differentiable, it must be continuous. I'm going to see that clearly down here. If a function is differentiable, meaning you can take the derivative, it must be continuous. Okay? Good. All right, that's first page done. We're on page 2. All right, some more limit questions. So this, for me, I kind of broke it down into 3 basic types. There's 3 limit questions. The first one is not a limit question, meaning that like, yes, it is written like a limit and it looks like a limit, but it's not a limit. They're really derivatives. When you see this, specifically h approaching 0, or like this form on the right where it's like the function minus the function with a point and like an x value minus that same point, if you recognize this, specifically h going to 0 being a giveaway, this is what I'm referring to. That just means take the derivative of x and plug in any relevant value. So you're taking the derivative of this or the derivative of this, and then plugging in any value. So in this case, you have to plug in the a. In this case, there may be a value, there may not be a value, it depends. So let's look at this question. So again, let's try it. So based on what I just told you, try this problem. Okay, hopefully you tried it. It's saying that the limit, so again, the key here, I see h approaching 0, boom, I'm thinking derivative. I gotta take the derivative of something. And so you should remember, okay, I'm gonna take the derivative of this function. So the function is ln x. So the derivative of ln x is 1 over x. And then I'm going to plug in that 0.4. So it's going to be 1 over 4. The answer is B. Okay, going good so far? Hopefully it's okay. Basic limits. Yeah, okay, so basic limits, these aren't really that common, but sometimes you get them. Basic limits just mean like, okay, limit x approaches 3 of like, I don't know, x plus 3 over x squared. And the really basic way that you solve is just plug in the 3, and it would be 6 over 9, which is 2/3. Okay. Now, you just knowing that is helpful. Maybe that'll come up, but like it's not the most common. Sometimes you have to factor stuff up and cancel. But in general, all of these methods can be overridden by the big one, which is L'Hopital's rule, which is like I am sure this will be on there, certain that this will be on the test. It's been on there for the last 4 years in a row. What L'Hopital's rule says is if you take the limit and you get 0 over 0, you can take the derivative of the top and the bottom and you do it again. You don't do quotient rule. You just take the derivative of the top and bottom separately. And you can keep repeating this as long as you still get 0 over 0. You can just keep doing this over and over again. But something really, really important to note, is that you can never say this statement right here. You can never say this. What you have to do is separate the numerator and denominator separately. You have to say limit as x approaches c of f of x equals 0, and then the limit as x approaches c of g of x equals 0. And then you say, since limit is indeterminate, use L'Hopital's. That's on an FRQ, right? That's not the case in a MCQ, whatever. Who cares? Nobody cares. Like you can do whatever you want. But in an FRQ, you must take the limits separately. It's very, very important. Take them separately. I'll remind you of this on test day. Before the test, I will say this. And then you can say, okay, L'Hopital, and then you write this. You're gonna write that, and then you'll do it again. And if you continue to get 0 over 0, you continue to do this, but usually it's good on the second try. Okay. Asymptotes and holes, removal of discontinuity. Yeah, there are definitely questions on these in the test. So we have a vertical asymptote when we have what? Hopefully you remember this, but it's when there's a 0 only in denominator. I'll talk about that in a second. We have a hole, also known as a removable discontinuity, which I talked about before. That's this. There's a removable discontinuity. And that happens when there is a 0 in both numerator and denominator. Okay. And we'll talk about that in a second. And then horizontal asymptotes happen when we take the limit as x goes to an infinity. So it can be this one, or it could be limit as x goes to negative infinity. Okay, and we'll talk about that in a second. We'll do some examples. So first one, identify any holes or vertical asymptotes. So here it looks like we have a vertical asymptote at 4, but that could also be a 0 in the numerator. So if you get a problem like this, you want to factor, if possible, top and bottom. So two numbers that multiply to get -4, add to get -3 are going to be x minus 4 and x plus 1. So we can see here, because this appears in both numerator and denominator, x equals 4 is a hole. If it was just, let's pretend for a second that it was just a denominator, that would be a vertical asymptote. See, 4 would be a vertical asymptote because it's non-numerator, but since it's in the numerator, there is a hole. Does that track? Make sense? Okay. There's definitely questions like that on the test. This is another one. Line y equals 5 is a horizontal asymptote to the graph of which the following functions. So when you take limits to infinity, there's 3 outcomes. you want to like, so we do limits to infinity. It's like a race, meaning like the biggest power wins. So the three outcomes I'm going to do this kind of below here, but the three outcomes are like the following. Either you can get like, you get something like x squared over e to the x, and this is limit x goes to infinity. And so e to the x wins. E to the x always, any exponential beats any power. So this would be 0. If the bottom wins, this is bottom wins. If it's a limit as x goes to infinity and it's something like, okay, x to the third over x, right, then the numerator wins. And that would be an infinity of some kind. So it depends on the problem. In this case, it doesn't really it doesn't have a it doesn't have a horizontal asymptote. It just goes to infinity. Does that make sense? So there is no horizontal asymptote because the function goes to infinity. And sometimes it can be plus or minus. It just depends on the situation. And then the last one is that where there's a tie. So if you think about limit as x goes to infinity of something like 4x cubed over 2x cubed, when there's a tie and it's the same power top and bottom, they essentially they cancel and you take the fraction of their coefficients, so it's 2. Okay, this is a tie. Okay, so back here in this one, if I'm looking for 5, if 5 is the horizontal asymptote, I should basically get a fraction of 5 over 1, or when I divide it, I should get 5. So you plug infinity in here, or like a big number, this doesn't work because sine just like goes up and down like constantly. It doesn't settle on a number. If I put infinity in here, it's going to go infinity. It's going to be like one of these. It's just going to go up to infinity, so that doesn't work. Here, it's going to go to 0 because it's going to be 1 over infinity. Here, it's going to, so the biggest power is 5x. The biggest power on the bottom is negative x. So the fraction there is going to be negative 5 because it's 5 over negative 1. This one would be negative 5. And then this one here, biggest power here is x squared. This biggest power here is 4x. So 20 divided by 4, right, is 5. So it's got to be E. Got it? Okay, that's it on limits. I'm keeping it kind of snappy. I'm trying to anyway. This might be a longer video than I expected. So words to phrases to look for. We're moving on to derivatives now, the meat of calculus. Words to phrases to look for. So when to think about taking the derivative. Slope of the tangent line means derivative at a point. Slope at a point. When you see equation of the tangent line, that's when you're thinking y minus y1 equals mx minus x1. We know this, guys. I've how many times have I said that this year? I don't know how many. But whenever you see the words equation of a tangent line or the line tangent, you would maybe want to think about writing that. That's fair to say. Other things, are rate at a specific moment, instantaneous rate of change, velocity when you're given position, or acceleration when you're given velocity. These are all moments where you want to take the derivative. Another one I would mention is like f of x, increasing, or is something increasing? That means take derivative and see if it's positive or negative. Okay, so I think of we'll do some rest problems later, but these are things to know. When you see these things, see the words like rate at a point or slope at a point, you're thinking derivative. Got it? Okay, it's 2 pages down. You're on the next one here. So common derivatives. All right, let's get through this. So you should know all these guys cold. You got to know them cold. There may be very, very easy questions, multiple choice. There could be one as easy as just like tan x. That could be one. Or it could be like tan x times cosine x. But you cannot answer that if you do not know the derivatives. And it is worth your time to memorize them and to make flashcards if you don't know them. X to the n is n to the x nx to the n minus 1. One thing I did not put here, but I assume you guys know, is that if it's a constant, it's 0. I assume that you would all know that. But in case you didn't, we got sine is cosine. We got cosine is negative sine x. We got tan is secant squared x. We've got cotangent is negative cosecant squared x. We've got secant x is secant x tan x. And we've got cosecant x is negative cosecant x cotangent x. E to the x is e to the x. A to the x is a to the x ln a. Ln x is 1 over x. And log x is 1 over x ln a. Okay? So if you could not knock those out at the speed that I did that at, if you couldn't go boom, 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 you don't know them. You don't know them, right? And it's worth memorizing them. It's worth it, guys. Cover it. I'm not there. I can't do it for you. You got to, can you do it? Can you do it? You got to do it. Chain rule. So if basic chain rule is a function inside a function. If you see f of x, f of g of x, right? Let's say this is h of x equals this, and you want to take the derivative. You take the derivative of the outside, keep the inside the same, and then multiply by the derivative of the inside. I mean, we've been doing that for a long time. It's all over the AP test. You need to know how to do it symbolically, but also like with a function. Go practice it on delta if you're not feeling good. This is big. Product rule similar, but it's multiplication. F of x times g of x. Whenever you're reading out a function, you see and you're like it's multiplying. You're not adding or subtracting. You're multiplying. You got to use product rule. You have to. H prime of x equals lefty right f of x g prime of x plus right d left g of x f prime of x. Whatever works for you, but definitely associate that plus with the multiplication of product, right? Quotient is division, right? Quotient is division. So whenever you see a fraction, so if h of x equals f of x over g of x, h prime of x equals, I remember it as low d high, g of x, f prime of x, minus high d low, f of x, g prime of x over low squared. I don't know, guys. Like just knowing these rules will like lock in problems for you. But if you don't know the rules or you mix up it at minus or whatever, you're just losing points for no reason. And I'm telling you, it's worth your time to memorize these and know them cold. Really know them. You don't know them unless you can write them from scratch. Like that's the reality, guys. You have to do that. Less common derivatives. Yeah, these are less common. I mean, they're sometimes on the test, maybe like 1 or 2 questions total. They're not a really big deal. I'd say like the ones that appear are like this one, and this one. So if you were just and sometimes they're written as integrals. We'll talk about that in a second. Um, if you're like at the stage where you got everything else down, I would look at these. There's a delta on this one on advanced derivatives. So take a look at that. And same thing with inverse function. I don't think I covered this at all in class. This was a delta that I gave over one of the expeditions or over a spring break. Similar thing, 1, 2 points maybe on the test, not really a big deal, but if you can get the point, it's a free point if you can get it. So if you're good, you're feeling good on other stuff, do this. But like these are not like do not do this if you don't know these. This is your top priority, okay? All right, implicit. We would have gone over this on the Thursday. So I'm recording this on Wednesday, so this would be tomorrow. We're doing this. So hopefully it's fresh in your head. Basically, when you implicitly differentiate, I'll just start by copying it. Xy plus minus x squared equals 4. You just differentiate across, but every time you differentiate y, you have to multiply it by a dy dx or a y prime, whatever you prefer. So it's going to be 3y squared y prime plus, and here you have to do a little product rule, x y prime plus y minus 2x equals 0. You get all the y primes or the dy dx's on one side. Lefty, right, was right. So that would be 3y squared y prime plus x y prime equals negative y plus 2x. Here all I'm doing is subtracting the y, adding 2x, subtracting y, adding 2x, if that's not clear. Then you factor out the y prime or the dy dx. The y prime comes out, so it's y prime 3y squared plus x equals negative y plus 2x. And then to get y prime completely alone, you divide. So 3y squared plus x, and then 3y squared plus x here. So that would be your answer. This would be the y prime. And sometimes it says, oh, evaluate the y prime at like a set of coordinates, and it'll give you 1, 2. And so then you would just like plug in those coordinates in here, and you'd get the y prime at that point. If it said find the second derivative, or in the FRQ sometimes it's like find the concavity, or see if the concavity is positive or negative at a point. You take the derivative of this again using quotient rule. So you use quotient rule to differentiate. And then you have to plug in dy dx again back into that, whatever you got. I'm going to take the time to do that. I'm going to just take the time to do that. So it's going to be, if I was differentiating this again, it would be low d high. So it would be 3y squared plus x. D high is negative y prime plus 2 minus high, which is negative y plus 2x. D low is 6y prime plus 1 over low squared, which is 3y squared plus x squared. What I'm saying is when you have to substitute it in is like you have to take the y prime, which is this, and replace that y prime with this fraction. I don't even have space to do that right now, but does that make sense? So this y prime would become this fraction. That's it. And this y prime would become that fraction. I'm just showing you that for reference. Okay. Moving on. Particle motion. Wait, or is that next, or is it? Yeah, particle motion is next. Very, very important. Oh, if I talk about things to memorize, holy moly, guys, I'm still losing my mind as I ask you these questions. Displacement, you gotta know it. If you don't know it, make a flashcard right now. Displacement is the what? To find displacement, you take the fill in the blank. Dora Explorer this. It's the integral from a to b of v of t dt. It's the integral velocity that's going to get you displacement. So it's giving you, remember, it's giving you a distance between 2 points. When we talk about distance, what I'm referring to here is like total distance traveled. So it's like the back and forth. So, I mean, if you just, again, want to remember this to this is this is A and this is B. That's displacement. If I, in blue here, went like this, I went like do, and then I went like back again, that would be total distance traveled, right? This is total distance. So like, let's say that displacement was like 1. Just say like that was like 1 foot. Then your total distance would be 1 plus 1. So that would be 2. And this one would just be 1. Does that make sense? Okay. I've gone over that a lot too. Distance, so to find distance is the absolute value. It's the same thing. It's the integral from a to b of the absolute value of velocity, because you have to count those backwards motions. Again, this is total distance. And then speed, again, got to know that speed is the absolute value of velocity. That's it. So speed, don't get like confused between like, as speed is like this fourth one. Speed and velocity are very, very closely related. Speed is just the absolute value of it. It's just always positive. Okay. All right, particle movement chart. We've done this, but it's good. Great review. You want to be very, very familiar with like position, velocity, and acceleration, and moving between the two. How do you go forward? How do you go backwards? I see it as forwards and backwards. You can see it however you want, but if I want to go forwards, I see it as forwards. From position to velocity acceleration, I want to differentiate to go forwards. And if I want to go backwards, I got to integrate. Okay. I don't have enough space to say that, but like if I want to go to left, you integrate. Okay. I hope that's clear from that. So yeah, so we have position, we have velocity, we have acceleration. You have s of x, or sometimes it's written as x of t or v of t. They have different letters. Position can be shown as s of x. Sometimes it's called x of t too, and same thing v of t or a of t. Um, the derivative of position is velocity. The second derivative of position is acceleration, or the derivative of velocity is acceleration. Got it? I mean, you should be very familiar with that. The units, um, the the position should be given in some like distance, like feet. Um, the units of velocity should be some distance over distance per time, so like feet per second. And then as you take the derivative again, it's distance over time squared. So it's like something like feet per second squared. Okay. All right, guys. Holy moly. You better know these. That's all I can say. You better know these. I've done my part. You got to do your part. Okay. The function is increasing. That just means like moving right or moving up. And that would be when velocity is, or the first derivative is positive, and I don't care about the acceleration. Decreasing is left or down, and that's when velocity is negative. We have a relative minimum, or sorry, relative maximum. That's like, it's also called a turning point. Both of these are turning, I'll write it here. Both of these are turning points, meaning like they're turning around these points. So this is, maximum is like right to left, or up to down. Minimum would be the opposite, right? Left to right, or down to up. And so again, so velocity equals 0 and is going from positive to negative, just like a relative maximum in functional analysis. Relative minimum would be when velocity is 0 again, it's going from negative to positive. And this is the second derivative test. If that's true, that means that acceleration must be negative, and here acceleration must be positive, right? If you think about it, you're going from negative velocity to positive velocity, then acceleration must be positive because you're crossing over, right? Critical points, this is like standing still. That's what it's called. It's just when velocity equals 0. That's it. Okay. Or undefined. Okay. That's fine. I'm gonna leave it like that. Inflection point is like changing acceleration. Um, that is again that is a relative extrema here. Min max, right? That's what that means. If that's not clear to you. And then here it's where the second derivative or acceleration equals 0 and changes signs. I'm about to do this like all over again, but without the um, without the particle motion aspect of it. Okay, if it's concave up, again, accelerate. If it's concave up, velocity is getting more positive. I guess you can just say velocity is increasing. Concave down, velocity is decreasing. Uh, okay, so then if that's true, then v of x must be increasing, and concave down v of x must be decreasing. Um, and then if it's concave up, that means acceleration's got to be positive, and if it's concave down, acceleration's got to be negative. Concave up, acceleration positive. Concave down, acceleration negative. Speeding up, what does that mean? So when v of x and a of x have the same signs, then it's speeding up. So if it asks you, is it speeding up at this point? You find the velocity there, you find the acceleration there, same signs, it's speeding up. If there are different signs, then it's slowing down. Different signs. Or opposite signs, whatever you want to say. Towards origin, it's similar if they are opposite signs. If the position, s of x, and v of x are opposite, it's moving towards the origin. If s of x and v of x are same, it's moving away. You want to draw it out if you're ever like unsure about that. Like if you draw it out, you like know where the zero is here, and like my particle's here, and it's moving to the right. If they're both positive, you can see it's moving away, right? Whereas if right here, you know, if it's both, they're both. If one's negative and one's positive, it's moving towards. Okay. Rate in, rate out. To get a quantity in or a quantity out, you want to just integrate the rate. Integrate r of t dt from some a to b, right? It's very similar to the idea of displacement, right? And the way I think about this is like displacement is a quantity of distance, right? You can think of that like displacement is like a quantity of distance. Well, if I want a quantity in or out, it's the same idea. It's like you're integrating that same rate. I hope you like make a connection between like the quantity in and the quantity out and displacement. It helps a lot. When I'm integrating, I'm looking for like oftentimes you're looking for a quantity of something, a quantity of feet, a quantity of pounds of what, you know, lemons, whatever. Okay, that will get you the quantity in or quantity out between some A and B. Amount in the future. So this would be weirdly I didn't talk about that here. Oh, that's wild. Okay, let me go back here for a second. In particle motion terms, a future position. Oh, that's crazy. I didn't mention that. A future position would be like x of a, or sorry, x of b, like some future position, is equal to like a current position, which is we'll call x of a, plus the integral from a to b of v of t dt. Ah, I probably should have done x's in there, but like it's not a huge deal. You see what I'm saying though? It doesn't really matter actually. Um, the t makes sense because I used x as my um, as that. So let me like label that if that's not clear. Like this is position at b, position at t equals b is equal to the position. You have to be given a position. So position uh, at t equals a plus like the displacement from a to b. I hope that makes sense. You know, I'm kind of making this video assuming that you have some prior knowledge and like you know roughly what I'm talking about. If you're like, you know what I mean? Like if you don't have any idea what I'm talking about, it's too late. Like focus on the stuff you do know. You know what I mean at this point? But hopefully this is ringing a bit of a bell because this idea is this exact same as this right here, the amount in the future. Like if I want a quantity in the future, Q of like B, right? It's the same as I need a quantity at A plus the integral of the difference here is like if there's a rate in and a rate out, you have to say that. So it's like R of t minus L of t dt from A to B. So I might like move everything down a bit, but like so this is like quantity at B at t equals B specifically is the quantity at t equals A plus like the net change from a t equals a to t equals b. And again, I hope that makes sense. A rate is increasing or decreasing. All you have to do, this is, I kind of talked about this in the derivative question. It's like you take, you know, is the derivative of that rate positive or negative? Like that's what you're doing. So if it's asking you if a rate is increasing or decreasing, all you're saying is, okay, is the derivative of that rate positive or negative? If, for example, if it was r prime of t and it was positive, it's going to be increasing, right? The rate is increasing. Um, if r prime of t is negative, it's decreasing. Okay. Absolute max or min. Um, this is where you set um, the rate in minus the rate out equal to 0. So the derivative of the the rate in minus the rate out equals 0. You want to find where the amount coming in, let me rewrite that so I don't confuse anybody. The rate in minus the rate out equals 0. When you find that, that is how you find your candidates. This is candidates test. That's how you get some of the candidates. Okay? And I'm about to candidates test in like a bit, so don't freak out. Okay? Next one. Function analysis. So this is the idea of this one, and I do want to cover something before I begin, is that it's going to give you a graph. There's always one of these questions, guys. It gives you a graph, and it's like, and this is this is f prime. That's what it's been the last 2 years. This is the last 2 years. It gives you f prime. Last 2 years. So what the prediction is this year is that it's not going to be f prime. And so it's like last year it gives you f prime and it asks about f generally. But what they're saying, the people, the predictors, what I'm hearing, I don't know, who knows. But what it could say basically is it could give you f of x, but it tells you that like, oh, there's this g of x, which is the integral from like 3 to x of f of t dt. So these are the same thing, but you just have to identify that, oh, really, g prime of x is f of x, so really this is just g prime of x. But you have to like make that connection before you answer the problems. Again, two versions. One is just like, okay, this is the derivative. It starts asking you about f. The other one, it's like, oh, this is f, and then we have this other function which is the integral of that. And then so you have to say, oh, well, the derivative of this um, is um, is that. And I hope that makes some sense. We're going to do an FRQ later where I'll kind of reiterate that. So don't worry too much if that's a little bit lost, but hopefully that seems familiar to you. So for key things in function analysis, when you do an FRQs, never ever ever use the words it. It is banned. No it. No like the graph. Jeez, I'd never ever want to see that. Be specific. Be specific, right? Use f of x. Use f prime of x. Use g of x. Use g prime of x, right? That's what we use. You do be specific. All right, guys. All right, take a second. We just did this basically with the particle motion. I sound like I do in class, don't I? This is how I sound in class. I'm frustrated even though you're not even here. Okay. Um, we just did this though. This is really, I need you to memorize this. I need you to know this. And I need you to make flashcards if you don't know this. Take a second, see if you can do it. If the function is doing these things right here, what is true about the first derivative? What is true about the second derivative? Take a second. Do what you can do. Really try. You're still waiting, huh? You want me to do it? All right, I'll do it. I'll do it. But I want you to pause and try. I do want you to pause and try. Here we go. It's increasing if the first derivative is positive. That makes sense, right, guys? Because what that's saying is the slope. Like, you got to think first derivative is slope, right? First derivative is slope. Second derivative is concavity. Get that in your head that the first derivative is the slope. So if the slope is positive, it's got to be increasing. It just makes sense. It just makes sense. The second derivative, the function is decreasing, the first derivative must be negative, because then negative slope, it must be decreasing. It just makes sense. Nothing is relevant here for second derivative. For relative maximum, what does that look like? A maximum looks like a little hill. So what's going on? At that point, right, we have a slope of 0. So we know that the derivative equals 0, but it's changing from a positive slope to a negative slope. So it's crossing the x-axis like that. Positive to negative. Okay. When we have a relative minimum, Same idea, but it's like down here. It equals 0, but it's going from negative to positive. Um, what is true about this? This is what's called the second derivative test. If you have a relative maximum, it must be concave down. The second derivative must be less than 0 because of because if your first derivative is going from positive to negative, then the second derivative, by definition, because the first derivative is decreasing and the second derivative measures the slope of the first derivative, therefore it must be less than 0. Okay, hopefully that made sense. And then this one is the opposite. It's got to be positive. Okay, look at it. That's concave down, is it not? Yes, it is. Is this concave up? Yes, it is. Okay, inflection point. This is where we change concavity. If that's not clear, change concavity. And so what's true here, this is the concavity function. So that's when the second derivative equals 0 and changes signs. And it's when we have relative min or max in the first derivative. You got to know it. Eat all of them. You got to know all of them. Okay. Concave up is when, again, this is a concavity function, so it's when the second derivative is greater than 0. Concave down is when the second derivative is less than 0. And it means, what does concave up mean? It means that the slope is increasing. So by definition, f of x must increase. And then here, f prime of x, am I saying it wrong? F prime of x must decrease. Say it, guys, if you're at home right now and you can talk, say it out loud, right? When you're trying to memorize it, say the words out loud. It will help you, right? Don't do it silently. Say, the function is decreasing when the first derivative is negative, when f prime of x is less than 0. It's a relative maximum when f prime of x, or the first derivative, is 0, and it goes from positive to negative, right? These two right here are the kind of the ones that are like less important. If I were to choose two that was like, okay, don't really worry about these are less important, but all the other ones, very, very important. Okay. Um, hopefully that's good. Hopefully we're clear on that. Concave up, remember that just looks like a U. Concave down looks like an N. When you go from a U to an N, that point right here is called the inflection point, where we change concavity. Just want to make sure that's clear. Okay. So okay, the next one, I'm not. Do I even bother doing it? The next one is what. Next one is referring to what I was talking about up here above. The idea of like, oh, they give you the function, and they give you like an integral of it, and you have to work it out. It's the same idea here. Um, the function is the integral, and the derivative is like the function f of x, and then the second derivative g of x is the derivative f of x. Um, it's the same exact chart again. So what I would do right now is I would close this. The only difference when you write this one out from memory is that instead of saying like f prime of x, like the other one was, just f prime of x, it's g of x is increasing when f of x is positive, right? So you know, on the test, what I recommend saying is when g of x equals f of x is positive. These two are the same thing, right? Again, that's what you need to establish at the very beginning if you have this kind of question. We move on. Candidates test. Okay, so candidates test. If you ever see the words like absolute maximum, absolute minimum, biggest, least, something like that, you make the table, you make your x, you make your function of x, you get the endpoints. Your candidates are endpoints and critical points, which, remember, that's when the derivative equals 0. You put them here on the left, and then you plug them in. Plug into function here. Okay? And we'll do an example just to make sure you're good on that. So, given this function, what's the absolute minimum? So, make your little table. We're going to have x, we're going to have f of x. I'm going to get my endpoints, which are negative 1 and 5. And then I got to get my critical point. So I'm going to take the derivative, and I'm going to set it equal to 0. Great thing to write on the AP test is just writing that. So we're going to do 3x squared minus 12x equals 0. We're going to factor out that 3x from that. So we're going to 3x is x minus 4 equals 0. So my critical points are 0 and 4. Both of those are on this interval. They're within the interval, so I got to do all these. So 0 and 4 are all in here. Then what all I'm doing here is I'm doing like my function f of x is x cubed minus 6x squared minus 4. So basically just have to find out what's f of negative 1, f of 5, f of 0, f of 4. You're not plugging it into the derivative, you're plugging it into the original function. So f of negative 1 would be that's negative 1 minus 6 minus 4, that's negative 11. F of 5, that's like 125 minus 6 times 25 is 150 minus 4, that's negative 25, negative 29. 0, 0, 0, this is negative 4. 4, 4 to the third is 64. Yep, nope, 50, yes it is, 64 minus 6 times 16. What is 6 times 16? 64 plus 30. I think it's 44, 96. I think it's 96 minus 4. That's minus 100. So 64 minus 100 is negative 36. So that would be my absolute minimum right here. So basically up here they would go negative 11, negative 29, negative 4, and negative 36. So what's my absolute minimum? That is the absolute minimum. And then it occurs at x equals 4. So sometimes they like, oh, is it the minimum, or like at what x value does the absolute minimum occur at? So you know the difference between those two. All right, moving on. We're getting there. I'm think I'm halfway through. Common integrals. So just like you need to know the derivatives, you need to know the integrals. And if you know the derivatives, generally you probably know the integrals. I will go over the fundamental theorem of calculus in a moment on the next page, so don't worry too much about that top. Basically, capital F of x is the antiderivative function, and so the derivative of the antiderivative gets you back to the original function. When you take the integral is the antiderivative plus c. Some very popular integrals that you need to know. Of a constant is just kx. X to the n is just O plus c. X to the n plus 1 over n plus 1 plus c. E to the x plus c. A to the x over ln a plus c. Ln absolute value x plus c. Negative cosine x plus c. Sine x plus c. Tan x plus c. Negative cotangent x plus c. Secant x plus c. And negative cosecant x plus c. One of the absolute key things about integrals, which I've been trying to reemphasize over and over again, is like when you're taking integrals, when you take the derivative of your solution, you should always get back to where you started. I keep on saying that over and over again. So if you're like, oh, what's the integral of sine? Is it cosine or negative sine? Well, remember, the derivative of cosine is negative sine. So this must be negative to undo that. Right? So if you know derivatives, you know you can get a lot of integrals. You don't know all the integrals, but you can get a lot of them. I talked earlier, I mean, hopefully that's clear. I talked earlier about inverse trig integrals a lot. Oh, no, I didn't talk about it a lot. I talked about inverse trig derivatives, and there's a few of those to remember. Sometimes these appear on the test. So I'll take a second just to go over this as like an example. Sometimes you will be given a really weird integral. It's like, and you're just like, I don't even know like what this is. Like I don't even know. Like I can't even do anything with this. You know what I mean? You're just like looking at it and you're like, what is this? Like I can't do u sub. I can't do anything. I can't do it. Like if it feels that way, look for an arctrig option. And if you can memorize these, it can sometimes just be a free point if you know what these are. Like which one's sine. So remember, this is just sine -1. This is tan. This is the same thing as that. This is the same as that. Okay. These are like the three that come up. So if you can just memorize these and know how to identify it, you can get a free point sometimes. Fundamental theorem of calculus. The idea here, there's multiple parts to it, and honestly, this is terrible for me to say, but I've kind of forgot which one's part one and part two, but it doesn't really matter. Um, the the main one is, well, like a big one. I think this is part two. Is just that the integral from a to b of some f of x dx is equal to big F of b minus big F of a. That's one of the key ones. So basically, take the antiderivative, plug in the b, minus plug in the a, boom. That's a key one. Sometimes on the AP test, what they'll do is it'll be like f integral a to b of f prime of x dx, and that's just little f of b minus little f of a. And you're just taking away that prime because you're just taking away that prime because you're integrating. It's the antiderivative, right? So the antiderivative at b minus the antiderivative at a is how you evaluate a definite integral. The part one is the idea that the derivative of the integral from some a, where a is a constant to x, of some like g of x, or it doesn't really matter what's on the inside, but that's just equal to g of x. So the derivative of an integral, as long as the key element to this is that this is just x, is just the inside. Okay, that's key. One of the key elements of calculus is that. So for example, down here I put this as an example. The derivative of this it's kind of a trick question. This is just, it's easy. It's just sine x to the fifth. Don't overthink it sometimes. That's it. But the caveat to this is the corollary to the fundamental theorem of calculus, is that if it's not x squared, notice this, it's not x. See how it's x squared? In this case, what you do is just take that x squared, you plug it in for t. So it's going to be sine x squared to the fifth times the derivative of x squared. So then times 2x. So it would be sine x to the 10th 2x. Be familiar with that. Properties of integrals. Really, the only thing two things I wanted to go over here was the idea that the integral from a to a of some function is just 0. If these two match, the integral is just 0. That's a big one. The other one is that if you have it in the wrong order, like let's say you had it was from b to a instead of from a to b of f of x dx, if you make it negative, you can flip them. That's another really important idea that comes up a lot. So that happens when you're doing things like with those function analysis problems and you're shading. There's also sometimes like multiple choice questions that use this where you have to flip them. It's always like a good idea to kind of draw it out and then you go from there. Okay. Blazing through it. Okay. 4 more pages. Table problems. This is all of calculus, guys, in one video, pretty much. How to approximate derivative using different quotient. Free point. Always, like very, very frequently on the test, basically they give you a table, they give you an x, they give you an f of x, and they're like, okay, approximate the derivative at this time or at this point, and so you find where like the midpoint of that, and you just take the AROC of that interval. And again, AROC, which I will go over in a second, is just f of b minus f of a over b minus a. So in this case, since 11 is between 9 and 13, it's f of 13 minus f of 9 over 20. F of 13 minus f of 9 over 13 minus 9, which is f of 13 was 21 minus 9 over 13 minus 9 was 4. And so that's 3, I think. Yep, that's the idea. And this is the same exact thing. It's just that sometimes it'll give you like the derivative here, and it's asking for the second derivative, but it's the same exact thing. You go look, okay, 6 is in the middle of these two. You do the AROC of these, and just pay attention to the unit. Sometimes it'll say, oh, like what units is it now in? And so you have to make sure you do that. Okay, you add another denominator. You multiply by another denominator. Okay, generally speaking. Riemann sum, yeah, this is always on the test too. So make sure you know the difference. When you're doing Riemann sums and trapezoids, the f of x's are, it's kind of confusing because trapezoid uses the formula for trapezoid rule is kind of confusing, but f of x's are like your height is where you get the height, and x is the width. So don't get those confused. So my widths here are 4 to 8 is 4, 8 to 9 is 1, 9 to 13 is 4. Those are my widths. So you can imagine those like the bases um, of my rectangles. And if it's a right Riemann sum, you just take the right f of x of each one, and that becomes your height of these rectangles. So you imagine like this is -2, and this is up at 9, and this is up way up at 21, right? And so you're getting the area of these. And if you're like ever lost, you just draw it out. Like don't freak out, just draw it out. So this would be -2 times 4 plus 9 times 1 plus 21 times 4. And just leave it unsimplified. If it's a no calculator section, just do that, right? So same idea for the left one, but you just use the left values. That would be 3 times 4 plus -2 times 1 plus 9 times 4. Trapezoid is the one that's a little bit more tricky. You have to know the formula 1/2 parentheses b1 plus b2 times h. And here the big idea is that the h is actually the width. It's really confusing. The formula is really confusing, and I kind of wish I just taught you a different formula just to make it easier. It's just because the way the trapezoid is kind of on its side, but really the h is the width, and then these are like the heights, if that makes sense. So for example, here, 1/2 would be that stays. B1 and B2 are these like my outputs, right? So 3 minus 2, and then the height is the 4, right? And so on. Okay, so it would be 1 plus 1/2, -2 plus 9 times 1, and then plus 1/2, 9 plus 21 times 4. Okay, that's trapezoid rule. With midpoint, midpoint is like the same exact thing, except they're 3 wide. So if it's a midpoint, you need like that middle value here. That's the only idea, right? So it's the same thing. The width is still, the width of this is 6. The width of this 10 to 14 is 4, and then it's the midpoints at -2 and 21. So this one's just -2 times 6 plus 21 times 4. Okay. Over approximation, under approximation. Yes, this comes up somewhat frequently. If it's a left Riemann, you can just draw a picture if you're not sure. Left Riemann, if it is decreasing, a left Riemann is an over approximation. You can see that there. If it is increasing, it is an under approximation. You can see it there. Other way around here. If it's increasing, a right Riemann is an over approximation. If it's decreasing, a right Riemann is an under approximation. For trapezoidal rule, it has to do with concavity. Again, just draw it out. If it is concave down, a trapezoid will give you an under approximation. If it is concave up, a trapezoid will give you an over approximation. Okay, this is CC up, CC down. Okay, got it? This is a common MCQ that I just want to go over one more time. It's one of those just kind of pattern recognition problems. It's not really, I mean, that's how I interpret it. Like I don't really think about the inner meaning. Me personally, I don't think about the inner meaning of this limit. Although I could think about it if I wanted to. I just remember like the pattern. The pattern is you got something over n, and that something over n is just a b minus a over n. So if it's 5 and 3, it's just going to be 5 minus 3 over n. So that's just 2 over n. And so I can immediately eliminate a and c because they should be 2 over n. And then this 3 right here should be the a of your like integral, which they both are here. But then it also needs to be adding the width too. So see how that's 2 over n. That's not 2 over n. So it's wait. Sorry. This is what I was looking at the bottom one. See how that's 2 over n and that's not 2 over n? It's going to be d for that reason. So it's the width here, and the starting point there. If you remember that, and you remember that the width is b minus a over n, you can get these problems. I think there will be one on the test. So, all right, theorems. 3 more pages. We're getting there. Theorems. There's more than 2 theorems. There's a third one called extreme value theorem, but it's pretty rare that it's on the test in any meaningful way. These are the 2 big ones, and I'd say MBT is like the biggest one to know. What does intermediate value theorem mean? Intermediate value theorem basically is saying like if you start here at like a, we'll call this f of a, and end here at f of b, then you have to hit all the y values between f of a and f of b. You like hit all y values between. I hope that makes sense. When to use it, generally like it gives you a function and it's like, does C exist such that f of C equals this number? So it's saying, is there some x value here such that it equals some y value? And if that y value is in this interval here, then it does exist. If this y value is outside the interval up here, then it does not exist. So the condition is continuity. You have to name that. And in general, you'll be given that it's differentiable. So you will say differentiable, and then you'll draw the arrow, and you'll say continuous. But the continuous is the one that you're looking for intermediate value theorem. It doesn't have to be differentiable, but it needs to be continuous. So that's the one you're looking for. You might get that from the fact that it's differentiable. Got it? So solution, basically like you find, as long as it's continuous, you find the like max y and min y in interval, also, which is kind of like f of a and f of b, right? And if f of c is between f of a and f of b, you're good. The sentence goes like this. That's not, you don't write that. You say, sentence goes like this. So you would say something like this: f of x is differentiable, therefore continuous. I'm generalizing here. It could just say that it was continuous, but from what I see, generally it says like differentiable. So you have to say, oh, I know it's continuous because it's differentiable. If it just said it's continuous, you just say, oh, it's continuous, right? So it's differentiable, therefore it's continuous on a to b. Um, f of a equals this number, and f of b equals this number, and f of c is between f of b and f of a. Therefore, there must be a c such that f of c equals this number on a to b. Okay. And if you're like stuck on this, you don't understand this, like go on YouTube, just look up intermediate value theorem examples, look up OChem Tutor, look up 3 Blue 1 Brown, look up all Turk's videos, like so many great videos out there. If this is not clear to you and you're like, I want to get this, then go watch it. Okay. Mean value theorem is even more popular than intermediate value theorem. It's a very similar but different. It's dealing with derivatives. It's saying like it's saying I can even draw a similar picture, that if this slope, the AROC, is m, right, then there must be a derivative that is on that interval that's also m. Okay, so if this is like your A and that's your B, there basically must be another another slope. Pretend those are parallel. There must be a tangent line that is parallel to that average rate of change. So okay, let me repeat that one more time. The average rate in an interval, and you find the average rate of change on an interval. There must be a tangent line or a derivative within that interval that also equals that same slope. A parallel tangent line. Okay, so when to use it? Generally, like it'll give you a function and it will say, does C exist such that f prime of c equals this number. And that's the key difference between these two. That the mean value theorem is asking about the derivative, and the intermediate value theorem is asking about the just a y value. This is a y value, and that's a derivative. Does that, you see that? The conditions are both differentiable and continuous, so you would need to say differentiable and continuous. Both need to be true. Okay. So if you see this on the test and you're just like, you're stuck and you just don't know what to do, you can get a free point just by find AROC to match the derivative. So that's just like f of b minus f of a over b minus a, and you want it to equal like whatever this number is. Whatever it says like the derivative should be. Generally speaking, if you just do that, you'll get a point for that, even if you can't write the sentence. And the second step is you say, okay, since f of x is differentiable, therefore continuous, usually you're going to say that, arrow continuous, um, and like the AROC from A to B is like this number, there must be a C such that f prime of C equals this number. Okay. Again, if you're like, I don't really get this, Mr. Kelly, like I just don't understand, like if you, it's kind of like on the hierarchy of things, it's like the next thing to do after you get those, the function analysis, the particle motion, the derivatives, the integrals. Like now, like, okay, trying to understand the theorems. All right. I am kind of losing my voice here. What was that? That was 15, so I'm on 16. What was that? Was it? No. Ooh, I got the back page here to do. Average rate of change versus average value, big concept, and I already been just talking about average rate of change just then. I'm reviewing this because so common I'm seeing a confusion between do I do this one or do I do this one? Which one do I do? And I think like key things to look for AROC, for average rate of change, you want to see the words the average rate of change of f of x. Like you are finding a slope of a function, the change of another function, right? Like that's really what you're doing here. Whereas with average value, it just straight up asks you what is the average blank, and it could be velocity, it could be acceleration, right? Like any of these words could be in there. Like I don't know, like rate, like any of these words could be popped in there, and then you do average value. But if it's the average rate of change of velocity or average rate of change of rate, like that is AROC. Okay, so the formula, you should know it. I just went over this. F of b minus f of a over b minus a, flashcard that. And then this one, 1 over b minus a, integral a to b f of x dx. There is a special situation, and I don't want to confuse you. So like if you're like, you feel like you're good on this, like just move on. There is a special situation in which like um, you would use average rate of change, even though it might seem like you should use average value. Let's say like you're given position, and it asks for average velocity. In this case, if it gives you position as average value, you might be like, oh, average velocity, that sounds like average value. But wait, you were not given velocity. You were given position. Do you see that? So this only works if you're given that. Like you have to know, you have to be given these, given the function, like that you want the average of. You see what I'm saying? Like if it says it wants the average velocity, you have to like know what the velocity is to do that. If it wants the average like acceleration, you have to know what the average acceleration is. But if you're not given that, so you're given position as for average velocity, that is average rate of change. You can get that by doing x of b minus x of a over b minus a. And so I just want to shout that out as like a kind of like a special situation. If it asks for average value and you have what it wants the average of, you just do that. If it says average rate of change, you do this. That's generally the rule. The only special situation is when it asks for an average something, but you do not know that something. You don't know the velocity. You're like, in this case, it's specifically position, and you do that. If you like, if this is tripping you out, just like move on. If you're the other one is like if you're given velocity and it asks average acceleration, this is another one. Um, Again, if you want average acceleration, you have to know the acceleration to do that. So you could take the derivative of velocity and do this formula on that because right, the derivative of velocity is acceleration. So you could take the derivative of velocity and do this formula on that new derivative, or you could just do v of b minus v of a over b minus a. That is average acceleration. Hope that's clear. Hope you understand that. If that wasn't clear to you, just stick to that top one, or you can call me. Give me a text to ask me, Mr. Kelly, explain that, please. All right. All right, we're last two pages. Area and volume. Boom. Okay. Area between curves. Easy. Top minus bottom. Don't overthink it. Top minus bottom. Dx a to b. No squaring, no pi, no nothing. I swear, guys, do not write that stuff. Okay. Or it could be right minus left. Dy. No squaring, no pi, no nothing. Leave it simple. Top minus bottom, right minus left. Okay, no reason to add a pi in there, no reason to square it. Must be bounded, must always be positive. Sometimes they switch positions, yeah. Okay, so if just be aware of that. What that means is like, oh, they can like go like this basically, and so you have to find that intersection point where they cross. So you might have to write two integrals to get that region. Okay. Disk method. The idea is you got a region, and you're rotating it around an axis, and it's flush. There are no gaps. That's a key idea. Like it's just flush with the axis of rotation. You can see that in the pictures here. And so it's just, again, integral pi a to b big R squared dx. The big thing here is why is there a pi? Because we're rotating. There's a circle involved. Right, that's kind of what I think. And squaring, as you get to volume, okay, now we're doing stuff. You got to square it to get the volume, right? Because you're adding up areas. Volume using the washer method, similar idea. It's just the fact that now there is a gap in that region. So you say this is your axis right here. Now there's a gap, so it's the same thing, pi big R squared minus little r squared dx from a to b. You can see images here to help you with that. You got to take the integral of that big region, that big shape, and then subtract the inner one. Volume is cross sections. This is just the integral from a to b of like the area of a cross section. Dx. That's it. That's all it is. Common ones are like semicircle, if I can write semicircle, which is like pi over 8 integral a to b x squared dx, where, by the way, x is like top minus bottom. Like that's what that means. Right? It's a vertical distance. Other ones, like you got like a square. It's a common one. That's just x squared. You got like the isosceles, right? Which is 1/2 a to b x squared, right? I gave you a sheet with all those on there. And then the other one that appears is the rectangle one, which is like the same idea as the square, except you add like a common multiplier. Okay, so check that sheet that I gave you. You know what I'm talking about with all the formulas on it. All right, we are nearly there. I'm in the home straight. This has been a marathon of a video. Let's do U-sub. Let's do a little U-sub review. So the one real integration technique that goes beyond just like basic integrals is U-substitution. For U-substitution, you need to like assign a u. When do you do U-substitution? I guess when you look in the integral and just like, oh, I'm like multiplying things. That's an indication that you got to do something. So sometimes you can like simplify this. Technically, what I could do is I could like square this and multiply it, like turn it into a bigger polynomial, and then do it from there. So like if you were more comfortable with that, like I would go ahead and do that. But like you won't always be able to do that. So in this situation, a U-sub is helpful because we're able to simplify the function you make the inside of a function u. So you have a big squared function, so the inside is 5 minus 2x squared. You get the derivative of that, du equals negative 4x dx. You get dx alone, so du over negative 4x equals dx. You sub it all in. Oh, in this case, you also got to put these, the 1 and the negative 2, into the u. So we're going to write a new integral. When a 1 goes in here, you get 5 minus 2, which is going to be 3. And negative 2 goes in, you're going to get 5 minus 8, so it's going to be negative 3. And then it's going to be 6x, and then it's going to be u squared, and then dx is du over negative 4x. So you're subbing everything in. This x will cancel with that x, so we have 6 over negative 4 out front, integral negative 3 to 3 of u squared du. Now we anti-differentiate u to the third over 3 plus, oh, I don't need to do plus c because it's a definite integral, negative 3 to 3. And then I can simplify this just to be 3 over negative 2. And so it'll be 3 to the third over 3 minus negative 3 to the third over 3. All of that times 3 over negative 2. Okay. So, I mean, I think that's just 9. That is 9. It's 18 right here. This comes out to 18. Divided by negative 2 is negative 9. Negative 9 times 3. So it comes to negative 27 is what I'm getting. Because you get this times this is that. Okay? All right. Last one, differential equation. All right. So with differential equation, it's the biggest question on the test. It's the biggest single question. By the way, I'm going to throw in my little secret right now. At the very beginning of this handout, if I can find the first page, it's here somewhere. This stack. I might need a second here. Well, on the very first page of this packet, there was a thing that said secret something, secret phrase. All right. Well, I want you to write there. If you're listening to this, you'll know what I mean. It says secret phrase on the very first page of this packet. On that line, I want you to write the words super legs. Super legs. Write that in that line. If you do that, I'll give you a little bonus point for that, because that means you're dedicated. You've been listening to this. You're at the end. Super legs. And that's a reference to, it's like a cycling thing. It's like when, I'll share that video with you guys if you haven't seen it. There's like in like the Tour de France and stuff, when like the cyclists are like there'll be people in cars following the cyclists, and they have radios on, and so like the cyclists are listening to their coaches kind of as they're like cycling, and like they shout encouragement at them like if they're doing well or something. And so one of the things they say is like, you have super legs, you have super legs. And so that's a joke with my friend, and we got like an engraving of that quote in when we were in France. I'll send you that video if you haven't seen my video, or the video my friend made of my cycling trip. All right, it's late, guys. I'm losing it. I'm losing it. Okay, here we go. Differential equations. This is the biggest point. This is generally worth like 5 points on the test, so you want to know this one. It gives you like a derivative like this, and like it gives you like a point, and it says, okay, solve it. Like find the solution. So to find the solution, first thing you want to do is separate. And you don't always do this. You don't always do the same thing, but oftentimes you do. 7x. Oh my goodness, guys, I'm losing it. dy dx equals 7yx. You multiply both sides by dx right here. Cancel, cancel. So you get like dy equals 7yx dx. To get that y over, you divide by y, divide by y. So you have dy over y equals 7x dx. Good? Good, because that cancels that, right? So that's 1 point, just for doing that 1 point. Then you integrate both sides, and generally you get a point for each integral. The integral of 1 over y is ln y, absolute value y equals 7x is 7x squared over 2 plus c. Generally, that's another point there, and that's another point there, generally speaking. But they're all, usually they're way harder than the one that I'm doing right now. Then you solve for c. So to solve for c, you take your point, which is 1 and 3. Okay, I'll do that, but I don't like it. I made that point up. Equals 7 over 2 plus c. So ln 3 equals 7 over ln 3 minus 7 over 2 equals c. So I just subtracted 7 over 2. Let me write that again. ln absolute value 3 minus 7 over 2 equals c. That's another point for doing that. So you plug in the points, plug in the x and y that you're given. This is your x, that's your y, and you plug that in to get c. Okay. Solve for y. So you go back to this part here, and you plug in the new c that we have. So it's like ln y equals 7x squared over 2 plus ln absolute value 3 minus 7 halves. And you're going to just exponentiate both sides here. This is all one big power. So y equals e to the 7x squared over 2 minus ln 3 minus 7 halves. And then the absolute value part of this, if you just look at it, you say, does this make sense? Well, if I'm supposed to get 3 when I plug in a 1, that looks like it makes sense, right? Because you're not going to get a negative value here. So yeah, looks good. That's it, and that's the last point. And like you'll see in videos that they'll do like a kind of different method, so don't worry too much about that. You can do it the way I'm doing it too. Okay, and you don't need to simplify it or anything more than that. All right, guys. Whew. That's not my last video because I got to do another one on the FRQs. So I'm gonna do another one of these right now, or maybe I'll take a break. But yeah, I'm really proud of you guys. And if you made it to this end of the video and it's Sunday night right now and you're stressing about tomorrow, I just want to remind you, it's all okay, guys. I'm super proud of you. You've worked so hard, and it's just a test, and you got your whole lives ahead of you. And work hard and do your best. And I'm so proud of you. But um, don't stress too much. Okay, don't go crazy over it. It's gonna be all right. You're gonna do great. Okay. I will see you on Monday morning for that breakfast. It looks like the bagels are popular option, so that's probably what we're gonna do. Rip my wallet. Okay. Bye bye.